Okay, so good afternoon, everybody. So I'm going to talk about quantum simulation, like Frank said. So the first thing that I want to do is to thank the organizers, Frank, and the members of the scientific committee for choosing this topic, and let me tell you about this topic. So, probably you have heard already or have seen in newspapers several times that the quantum simulation is the obvious application of quantum computation. No, there are many tasks for which we think that quantum computers will help us, but there is one that everybody is convinced that it will be like that. That's quantum simulation. And in particular, some people even think that quantum simulation may be the first one, in the sense that already with existing devices or the ones that are planned, then we will be able to solve some problems that have some practical, in quotes, use that we cannot solve with classical computers. And so this practical use that I say in quotes, practical, at least from the scientific point of view, that would solve some scientific problems that we cannot solve with classical computers, or even better, will help us to develop better theoretical techniques or even classical algorithms to understand better some of these scientific problems. And so, in fact, it's a little bit paradoxical that it seems that the very big applications of quantum computation, the ones for which we have exponential speedups, are on the one hand cracking numbers or cracking, let's say, some cryptographic codes or cryptographic methods, and the other one is for scientific research. But if you go back 80 years, and you look at that time, the people who were building the first classical computers, what are the only applications they had in mind? There were these two as well. They used these classical computers to crack codes and also for scientific research. And so I'm going to talk about here how to use quantum computers and quantum devices for scientific research, and in particular for solving many-body quantum systems. So the field of quantum simulation tries to solve these problems, and so there are many problems of that kind that appear in physics or in chemistry, and so here I will concentrate on those that appear in physics. So actually the quantum simulation is a very broad field where there are many people working with many different methods, but there are some particular problems, the ones that at least I know better, that are physics problems, that we don't have good methods, good classical methods to solve, and with quantum simulators, then we hope that we will be able to solve. So I'm very aware of the fact that here you have a very and diverse audience, in the sense that there are people coming from computer science, maybe from math, from physics, chemistry, engineering. And so what the goal of my talk is to give a little bit of each part of the talk to each of these communities. So for the computer scientists and mathematicians, then I want to explain what are the problems that are interesting in quantum simulation, the physical problems that are interesting, why they are interesting, how do we formulate them in physics in a relatively sharp way. For the physicists, I will tell about quantum algorithms that people are used to solve these problems, or that people have developed to solve these problems, and some of them are currently being used, or at least tried, with some of these quantum computers. And the talk will be part of it will be first to set up what are the problems that are interesting from the physics point of view. Then what are the quantum algorithms that we know, and so when they are, let's say, efficient in solving some of the problems. And then if I have time at the end, I'll talk about something that is a little bit more weird in the context of quantum information theory, which is analog quantum simulation. So, in fact, it may well happen that the analog quantum simulators are the first ones that have some real killing application of quantum computers, or analog quantum computers at least. And so, if I have time, I would like to tell you a little bit about analog quantum simulations, because I personally believe that those are the ones who can solve many of the problems that I will pose better at the moment than digital quantum computers. Now, maybe also as an introduction, just to say something that you probably have heard, all of you, that the first time that quantum computers appear were in the context of quantum simulation. That was, Richard Feynman, in his famous visionary paper in the 80s, when he realized that at that time, so people were trying to solve problems in high energy physics, actually, so they wanted to have problems in quantum chromodynamics, so to know how the nuclei behave and what are the forces inside the nuclei. And they realized that the theory they had, if they wanted to put it in a computer, they could not solve it because, the scaling was very bad. And this is why he proposed at that time that in order to solve these problems that appear, in that case, in quantum field theory, the first thing that you will have to do is to discretize space and time. And at that time, so people were already talking about lattice gauge theory, so this was a framework. But if you discretize time and space and try to predict, so what will be the physical properties in quantum chromodynamics or high energy physics, then this will take an exponential time. You use a classical computer, but if you had a quantum computer in which you would use qubits and gates, basically, is what he was describing, then for some of the problems, they can be solved much more efficiently. So in fact, he has this statement that says that, it's not natural to solve classical quantum many-body problems with classical computers, but let's do it with quantum computers. And so that's what is the plan. So the plan is first, to tell you about the setup, so how we formulate these problems in physics. And so I'll mention also some motivations coming from physics, why these problems are interesting. And then I will end up just trying to sharply formulate what is the problem. So giving some lattice, giving some Hamiltonian, which is defined in some particular way, and giving some other parameters. You would like to compute something with a precision epsilon and blah, blah, blah. And so that's the way that is the formulation that leads then to quantum algorithms to solve these specific problems. I will tell you about some problems in dynamics. So you want to know if you have one of these quantum many-body systems and you shake it, so what will happen in the future, so how the physical properties of the system will evolve. Or if you're in thermal equilibrium, so you like to know what are the physical properties at certain temperature, or even at zero temperature. And and then in the third part, once I introduce these algorithms, I'll tell you about the difficulty of many of them, and so with their, polynomial time and things like that. And then, if I have time, I'll talk about analog quantum simulation. So one thing that, of course, for many of you that you have studied quantum computing, that you know very well, is that if you want to solve some problems in quantum many-body physics, these are QMA hard, so not even a quantum computer will be able to solve it. What I want to put here is a little bit of touch of physics, because the problems that are described as QMA hard are not the problems that typically appear in physics. In physics, there are problems that nature is able to find the ground state, to find the thermal state, and this is why we see things. And therefore, this means that there should be some efficient quantum algorithms, let's say nature, that evolves it. So they're very special problems. And so I'll spend some time here also to mention so that in the physics problems that we're interested in, so they are very special. And so even, the general problem of finding some physical properties in the ground state or low energies and so on is very difficult. So for some physical problems, there are extra conditions, there are extra promises that allow them to solve them in polynomial time. Okay, so that's the setup. So I'll start, and as just mentioned, so I'll use the blackboard. So I'll try to write sufficiently big, and I think that there is a camera which will show for the people who are in the back. So it's at some point you cannot see something, then just let me know and try to write a little bit bigger. So I have different sizes there. I'll try to accommodate to some of them. And the other thing is that I'll do like the previous speaker. So I will just talk, and then once in a while maybe I ask you if you have any questions, and then I'll proceed like that. Okay, so I start first with the setup. And this will be some setup that I will be interested in. And that's not the unique, but this is the one that I'm concentrate here. And I know many physical problems which correspond to this setup. So the first thing is that I will have a regular lattice. And so I'll have something that I'll typically describe or draw in this form. And this is because in problems like they appear in condensed matter physics or material science, So there is a lattice structure, a physical lattice structure, and now we want to study what happens with electrons moving there. Then they move like in a lattice. So that's already described in a lattice. So the Hamiltonians that we write are in a lattice. If you work in some other fields like high energy physics, then space is continuous. Then you discretize it and you solve it on a lattice. So that's why we typically work with lattices. And these lattices are regular lattices, could be square lattice like the one that I drew here, triangular lattice, many lattices, but most of the time just take the square lattice. Now, at each of these vertices of this lattice, then we have an object that we typically in physics call spins, or can call electrons, or something like that. So for the moment, let me associate a Hilbert space of dimension d, so to each lattice size. So we have a qubit in each of the lattice size. And right, so now there are more general problems. And so, for example, so people sometimes work with fermions that I will introduce in a second, but that's not the only one. So if we work with these finite Hilbert spaces, we typically say in the physics jargon, these are spins. If they are particles that hop and that have some special properties, they are fermions. And there are some cases, like in lattice gauge theories, where you have a mixture of them. So you have both spins and fermions. And for example, typically in lattice gauge theories, so what happens is that the lattice, even though you draw it as a square lattice, then you put also variables in the links. And what you have is that in the vertices of your lattices, you have these particles that I'll describe properly in a second. These are fermions. And on the edges, you have these spins, or even bosons. And so that's the first thing, that's the physical setup that we have. That there is a Hilbert space. The total Hilbert space would be just total, write it like that, will be just the tensor product of all this with all the vertices of the lattice. And if you have now all the degrees of freedom will be different, but that's the typical setup that we have. Now, we can have finite lattices, infinite lattices. So as I'll mention later on, many times in physics, we are interested in what is called the thermodynamic limit, that I'll define later on as well, but in which case we start already with an infinite lattice. And we'll ask properties, I mean, some questions about this behavior of these spins in these infinite lattices. Sometimes we say that we have periodic boundary conditions. What it means is that we identify, let's say, the spin that is here with the spin that is there, and the spin that is here with the spin that is there, in such a way that we have like a structure that is a torus. You can imagine that you have like a torus, and then you put a lattice on the torus, and so on. So there are many possibilities, but what I'm going to explain will apply to all of them. This is why I don't spend so much time now here giving you all the possibilities, but just that you know. Okay, then the second part, apart from the lattice, then we have the Hilbert space of the spins, and at the end we're interested in predicting physical properties. So physical properties, this means that we have some observable, we have some operators that are acting on these spins, and so we are interested in some expectation values of these observables. So typically we define local observables. So for example, if I have one of these vertices here, right, which has this n coordinates, so it's somewhere here, and let's say corresponds to this lattice, then I'm interested in something that I can call like On. This is an operator which acts trivially on each of the lattice size, except at the nth lattice size. And this is what we call a local observable. And so what we want to predict is, given some conditions, given dynamics, given thermal equilibrium and things like that, so expectation values of this kind of operators, local observables. So we like to compute things of this sort. But it will be like if you have a density operator, this would be On times rho. Or maybe you have two observables, On, Om. You would like to compute this expectation value. And this is what we call correlation functions. So you have an observable on one side, another observable in another side, another operator, and then you would like to compute these quantities. And sometimes we even subtract the expectation values of each of them, and this is what we call connected correlation functions. Okay, so it's right. So those are the observables. Now there is a very special kind of observable that is in physics that appears very often, which is called Hamiltonian. And the reason is that the Hamiltonian in physics is in charge of two things, has two objectives. So first of all, it will tell you how is the dynamics of your system. So it will allow you to predict how the system evolves with time. So it generates the dynamics, so we will see in a second as well. And on the other hand, if you have what is called thermal equilibrium, it will tell you what is the state that you have. So this has a very special role, it's some special observable. And so typically when you have a physics problem, people have already identified the lattice and will tell you what is this Hamiltonian. And this Hamiltonian is either derived from first principles, like in lattice gauge theories, you have the standard model, and out of the standard model you discretize it, and it comes something like this Hamiltonian. Or if it's in condensed matter physics, so typically these are phenomenological, so people see that some things happen and then they guess a Hamiltonian and they give you this Hamiltonian. And the goal is then, given the lattice, given the Hamiltonian, given the situation that you have, either dynamics or thermal equilibrium, or they will ask you about some observables and will ask you to compute these observables, these expectation values, with certain precision. I'll go back to that, okay, so just saying. But anyway, so the Hamiltonians that I will consider here would be Hamiltonians that can be written as a sum of some Hamiltonians, and these ones here are what I will call geometrically local. So what this means is that this operator that is here, it's one operator of this kind, however, is acting on a region of the lattice. So for example, it could act on some, let's say, on this region, one of them. The other one will act on this region, the next one on this region, and so on. So we will consider here now what are local problems. So the Hamiltonians only has some range, and the range is finite. It only acts on certain, let's say, spins around one, and then these are different for the different spins. So here we sum to all the vertices of the lattice, and then we have Hamiltonian acting around the spins that are the vertices, and they are trivial in the other places. So why do I consider this kind of Hamiltonians? These are called in physics local Hamiltonians. Well, first of all, is that from first principle, all the Hamiltonians in nature are local. I mean, this is ensured by the theory of relativity, that we have locality in physics. If this was not true, if there is a Hamiltonian from first principle that doesn't have this property, then we could violate relativity, so we could violate causality, and there are many problems caused by that. So that's the first question. Now the second is that if we are talking about condensed matter physics problems or solid state physics problems, so many of these problems are well described by local Hamiltonians. There are some other ones that are not. These effective Hamiltonians, so these the ones that appear in condensed matter physics, they are phenomenologically. They are not let's say, fundamental problems. So you would like to get what is the Hamiltonian of a material starting from the standard model, you will have to start eliminating degrees of freedom and doing approximations, and you will have an efficient description with a Hamiltonian that does not necessarily have to be local, but still I will assume that this one is also local, because this allows also, I mean, many of the problems that appear in condensed matter physics, we have local Hamiltonians of this kind, most of them I would say, but it also, I mean, this Hamiltonian inherits some properties that are interesting when we talk about complexity simulations and things like that. Okay, so we have lattices, we have Hamiltonians that are local. So many of the Hamiltonians that appear in physics are translationally invariant, are homogeneous. So this means that the Hamiltonian, this operator, is the same, however, it's translated. So we have an operator acting around one of the spins, and then you take the same operator, translate it on the lattice, and that's what this sums. So in that case, we say that we have translational invariant. Or people use in physics jargon homogeneous problems. And you will have translational invariant in all directions, so you're in 3 dimensions, in the 3 dimensions. And that's an extra property, and sometimes I will use it, and sometimes I will not use it, and I will make some difference about them. Okay, so I start now with some examples. I have not formulated the problem yet, but for example, typical Hamiltonians. So let's take 1D, and the Hamiltonian could be something like that. This is what is called an Ising Hamiltonian, and where this just means that the sigma c operator acting on side n of a one-dimensional chain. There's a one-dimensional lattice, and n just gives you what is the coordinate in this chain. And so here you can see already that I have assumed periodic boundary conditions, so I have identified the nth capital nth plus 1 with the first one. And so that's a typical Hamiltonian. And that's so simple that all the questions that I'm going to ask can be solved exactly for this problem. So it's very, very simple to deal with. Now, another problem could be, let me write it in 2D. Okay, so it's similar to the previous one. And now this symbol means that the sum is extended only to the values of n and m that are connected by a vertex by a edge in your lattice. So these are what we say nearest neighbor interactions. That's called the Heisenberg model. And you can add terms like that to the Heisenberg model, and you have different versions of the Heisenberg model. You can also have Heisenberg models in which you change the signs here and there according to some patterns. I'm not going to say that, so maybe, this is negative, 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 the signs that we change here and there, and they correspond to different, let's say, physical situations, and it turns out that the Heisenberg model, for example, to answer some of the questions that I will ask later on, can be done efficiently with Monte Carlo methods. However, if you start changing signs here and there, then it's much more difficult to what we have. I mean, it was mentioned that there is a sign problem for this problem. Okay, you can also go to 3 dimensions. Maybe another problem is this. So this also has a name. It's called Hubbard Model. It's the simplest version of the Hubbard Model, where you see that now there are operators here that I'll define in a second. These are called fermionic operators, and they describe the motion of fermions in the lattice, electrons in a lattice. Air, n, and m are the coordinates in the lattice, and sigma is what is called the spin that takes the value, so maybe I should write it here. Sigma can be either spin up or spin down. So these are electrons which have a qubit in it, there's a spin, and they move on the lattice, and this term describes the motion, and this term describes the interactions of the electrons with each other. So here, I have introduced some operator, and these are fermionic operators. So these are operators that, associate each of them to one of the lattice size, and then they fulfill anti-commutation relations. Of this sort. Well, this parenthesis, or this way, so AB is just the anti-commutator, AB plus BA. Okay, so these are a little bit strange objects, because two operators on different sides don't commute, they anti-commute. So if they were spins, then they would commute. Whereas here, they don't commute, and this makes things a little bit more complex. However, there are ways of converting these operators into spins themselves. Typically, you do it very naively, then you have a price to pay with that, namely that the Hamiltonian, you just translate this Hamiltonian into spins, it will not be local anymore. However, there are also ways of translating these problems into spins with Hamiltonians that are local, in which you have to pay a little bit of a price, so you have to double your system and things like that. But anyway, so that's another problem that, typically appears. This is a very important Hamiltonian in condensed matter physics, so that's what is behind most of the descriptions of electrons moving in material. So when you have conductivity and magnetism, then it's related to this Hamiltonian or generalization. So maybe here, now, this term doesn't have nearest neighbor, but also next near neighbors, and maybe this term here has now more spins. These are different bands, and so on, but they have the same kind. And I will not write it here, but I mentioned before, so that you have problems in high energy physics that are also very difficult to solve. There are problems in which the Hamiltonians look very much like those. However, you also have degrees of freedom on the edges. So this means that you have now, you want the spins on the edges. And so what happens is that here you have some spin operators acting, and then you have some other terms, some other Hamiltonians maybe of this kind of spin operator. So these are like spins interacting with electrons. And these spins can have a dimension which is very large, can have infinite dimensions. So the D, the dimension of the Hilbert space of the local spins, can be infinite because these are bosons and so on. But anyway, so this gives you an idea of the kind of problems that we are formulating here. These are lattices, regular lattices, with Hamiltonians that are locals, and we can have typically either spins or fermions or combinations thereof. And right, so these kind of problems describe magnetism, magnetic materials, and these kind of problems correspond to electrical properties and also magnetical properties. So actually, from these problems, sometimes you can reduce when the motion, when the electrons cannot move, to this problem here, so they are related with each other. Okay, so another thing that is important is, because when we look at the difficulty of solving these problems later on, so we want to look at the Hamiltonian, and in particular at the spectrum of the Hamiltonian. So the fact that the Hamiltonian is local means that the eigenvalues of the Hamiltonian are not completely random, so they have some specific form. And so that's why so maybe let me just introduce here, just to make things simple. Let's normalize these Hamiltonians. You can always multiply by a constant, so let me assume that h lambda, the norm, is smaller or equal than 1. Okay? So that each of the terms, you have n, a lattice with n lattice size, and then you have, therefore, n of these Hamiltonians, that each of them has this property, because you can always divide the Hamiltonian with a constant. This just redefines time later on, so that's not so important. And so with this condition, then we can make some statements about the spectrum of the Hamiltonian. So we know first that if we plot here the possible eigenvalues of the Hamiltonian, so we typically write like this: En is equal to En. So the eigenvalues will run from -n to n, where capital N is the number of lattice size that you have here. And so there will be maybe one eigenvalue, which is the minimum eigenvalue, and the corresponding eigenvector, we call it ground state of the Hamiltonian, ground state, and this we call ground state energy. And then we will start having some other eigenvalues, and in total, the number of eigenvalues that we have is, we have a Hilbert space, which is the tensor product of n of those. If each of them has dimension d, then it will be d to the power n. So what we have is between minus n and n, there are 2 to the n or d to the n values, eigenvalues. So they will be concentrated. There will be many. And so what you can show very easily is that most of them are in the center. So you can just now define, what we call density of states. You just take some interval that you call epsilon, and then you just take here and count, so how many eigenvalues are in this interval, then here, then here, then here, then here, then here, then here. Then you make a histogram. And so this would be what is called the density of states with some interval epsilon. You can plot it continuously. And so this is minus n, and this is n. So it will be something like that. And it's very easy to show that because these Hamiltonians are local, then the width of this density of states scales like square root of n. So again, the fact that we have problems that are local automatically implies that the spectrum of our Hamiltonian is very peculiar. It has many of these eigenvalues in the center. And in fact, if we make our system bigger and bigger and bigger and bigger, then you see that all of them are concentrated in the center. So we would now plot the same quantity, but as a function. So this would be E, like the eigenvalue, E divided by n. Then we will have something like that. And this would be of the order from -1 to 1. And this would be 1 divided square root of n. So as we are increasing now the size of our system, then this is getting narrower, narrower, narrower. And as we will see in a second, so typically we will ask about properties of the spectrum somewhere here. And you see that here we'll have very few eigenstates, and that's why it gets very difficult. Most of the eigenstates, you take a random state, it will be here. And so we'll have to find properties that are the physically interesting, which are somehow lying at the edge of the spectrum where there is an exponentially small compared to the total one number of states. So getting there will be difficult. But anyway, so that's also another property of this, let's say, Hamiltonians. Because they are local, they have this property. Okay, so now once that I have defined Hamiltonians, I want to talk about the states. Okay, so I said that we're interested in the physical properties, but we want to know also what are the states that are interesting from the physics point of view. So this would be now states. And so we typically are interested in two kinds of states. First are the ones that are obtained through dynamics. So you start with some initial state, psi0, which this typically will be one state which is easy to prepare, so it could be something like a product state. And then you're interested in the state which is evolved with evolution generated by your Hamiltonian. So this would be psi of t. So this corresponds to the dynamics. So you start with some initial state, which is prescribed, all the spins down, and then your Hamiltonian still acts and start creating superpositions and entanglement, and that's the state that you're interested in. And as I will formulate more sharply later on, we will be interested in the expectation values of some of the local observable of some correlation functions in the state that has been evolved after some time t. So that's number one. The other ones are the ones that correspond to what we call in physics thermal equilibrium. They are given in terms of what is called the Gibbs state, where beta is just a constant. Beta typically is called 1 over T, and T is called temperature. And as you see, this is now a mixed state, which is also described in terms of your Hamiltonian, and another parameter which we call temperature. And so in physics, so if you study statistical mechanics and you have an object and then you let it for a while, then one of the postulates of statistical mechanics is that the state of that object after some time, when it equilibrates at certain temperature, is described by this state. And this is called Gibbs state. And here, you already see what I told you before, that the Hamiltonian in physics, this operator that I told you before, that is coming either from first principles or it's coming from the phenomenology, has two roles, plays two roles in quantum physics. First of all, it generates the dynamics, but also describes thermal equilibrium. So when you don't touch anything and just wait, then this will be the state of your system. And so that's called thermal equilibrium. And so we typically want to make predictions about our systems when they are in thermal equilibrium or we have evolved after some time. There's some particular case of these density operators, which is what happens when the temperature goes to 0. So you can take the limit here when beta goes to infinite, and then you see that this will be projector into the ground state subspace of your Hamiltonian. And so this is what we call the ground state. It's the one that corresponds to the minimal energy that may be degenerate or not. And so this is the state. This is the ground state. I mentioned it before. And so these would be problems which correspond to thermal equilibrium at 0 temperature. Okay, so maybe now to make a little bit of contact with what I said before. So this problem here, you see you have an e to the minus beta h, and this h, actually the norm of this operator scales like n. So you see that as long as this is a constant, so you have certain temperature, then the trace of this operator, whatever is in the denominator, would be e to the minus beta n, or something like that, would be exponentially small. And so you'll say it later on when I talk about quantum algorithms, that if you want to create this state, and then you're naive, then you can do it with a non-unitary evolution, just by measuring, but the probability that you success would be exponentially small. So that's why it's hard to get it, unless you're here in the middle of the spectrum, but here it's completely uninteresting because this corresponds to infinite temperature. So here everything is very simple. And in fact, now you can, I mean, I'm not going to do that, but you can just take now what is the distribution of energies of this state. So this is not an eigenstate, say it doesn't have, it will have certain variance. You can compute what is the variance of this density operator in energy and the mean energy. So typically it will have some mean energy which is here, and so maybe it's here. Okay, so this would be like the mean energy. So it would be the trace of this rho times h. That's the mean energy of a state at certain temperature. And you can compute the variance, and the variance again also scale as a square root of n. And so you see that when you're talking about finding properties of density operators at certain finite temperature, you are interested in computing properties at the edge of the spectrum where there are very few states. You're interested in the, let's say, the eigenvectors in this area. If you're at 0 temperature, you're interested in this one here. And there are very few of them there. So whenever you want to find a quantum algorithm that goes there, you will have here a bottleneck, because you will have to go over an exponentially small states and you'll have to land there. And so you have to find ways around this problem. Okay, so if I didn't forget anything, I think that we have now all the ingredients to formulate, what are the problems that we want to solve. And so, continue here. So this would be like the formulation of the problems. Okay, so the first is about dynamics. So we want to predict what would be the physical properties of my object. This could be either high energy physics problem or a condensed matter physics problem or so on. And we want to know how they evolve. So typically we will be giving a lattice. Then we are giving some number of qubits or spins in the lattice. Then we are giving some initial state, which is easy to prepare, psi 0. Then we are giving some time, t. Then we are giving some observable. And then we are giving some precision, epsilon. And so what we would like to do is to compute what is the expectation value of this observable, which could be local, could be one of these correlation functions. So typically it will be either 1 or 2. So we like to compute what is this expectation value. In such a way, this is my output, output, in such a way that this is smaller equal than epsilon, where psi of t is just what I told you before on that lattice. And so typically, you see, this is what you want to give. You want to give a value, a number, that is as close as possible, up to a distance epsilon, to the real expectation value, and you like to do it with a state evolved from the initial state that you have been given up to some time with a Hamiltonian. I forgot to say it here that there is a Hamiltonian also, of course, on that lattice. Okay, so that's the problem. And now, so typically, now you could solve this problem with a classical algorithm. There exist classical algorithms to solve this problem. However, in this full generality, all of them scale exponentially with n, or exponentially with time and n, and things like that. And whereas now you solve it with a quantum computer, then it will all scale basically linearly with n and linearly with time. So this is why this problem, as formulated in this way, can be solved much more efficiently in a classical computer, in a quantum computer, than in a classical computer. Just to remark this a little bit more. So imagine that you start with some initial state, and at the end, this psi of t, you would like to write it in some basis, in the computational basis. Then at the end would be a linear superposition with all your spin states. And you see that if I want to solve this problem, classically, I will have to find all these complex coefficients, first of all, and since there are exponentially many with n, then I will need an exponential memory to store all of them, and I will have to do one operation with each of them at least, so it will take exponential time. So both we will need an exponential memory and exponential time, and with this then we will have to compute this expectation value. So with brute force, that's the problem that was identified already by Feynman many years ago. There's the exponential growth of the resources that we need to solve quantum problems with classical computers. Whereas in, as we'll say, a quantum algorithm, what we'll do is that we'll prepare in a quantum computer this state, we'll measure this observable many times, and take the average value, and the average value will get as close as you want to this one here, and this is why it will be efficient. Okay, so that's the first problem. The second problem would be the ground state problem. So you're giving, again, the same thing, except for this and this. And so what you would like to do is to compute up to error epsilon, the expectation value of psi 0 or psi 0 minus, this is the one that you give, the output, up to epsilon. And this problem, then we know that formulated as a decision problem, if you don't put constraints, so your h lambda, even if they are local, they can be arbitrary, we know that this is QMA hard, this problem here. You formulate it properly. To know whether, for example, if there is an energy below some number or above some other number, and so on. However, as I will mention later on, it turns out that many of these problems that are here, that I mentioned here, actually, this can be obtained with certain algorithms, and because they fulfill certain properties that are very special for those states. And therefore, that's something that can be done with a quantum computer or a quantum simulator. However, classically, even under the same conditions, we don't know how to compute these things. And that's why, for physically relevant problems, we may have a quantum computer that would solve these problems. And then there are this thermal equilibrium, which is the same formulation. Now you're giving, again, the lattice, n, o, epsilon, and h, and so on, and you're giving an extra parameter, which is temperature, and then the idea would be to compute trace of rho Gibbs O as close as possible, like that, where this is this Gibbs state, is e to the minus beta h divided by the normalization. So C, I forgot to say that is the trace. So maybe I go here. And so this C, this is just the trace of e to the minus beta h in such a way that the operator is trace 1. So before I finish this part, this would be like the formulation, I wanted to make a couple of comments that I think that are also relevant for what I want to say later on, is that, so what are we really interested now in these physical problems that we want to solve with these quantum simulators and that we cannot solve with classical computers? So typically what we have is that now our Hamiltonians depend on certain parameters. You saw it in the examples that I wrote there. There is one parameter which was this h, another one is the u. So at the end, what you'd like to know is if you plot here some of the parameters, then maybe, so one of them could be temperature, the other one could be this u, or could be any other one. Then you would like to know, so what are the physical properties that you have for different values of the parameters? So for example, you would like to know if there is magnetization, if the material is magnetic, or if there is a superconductor. If now you compute some expectation value, the expectation value is different than 0. That's this kind of properties. And so what happens normally is that as a function of the parameters, then you have different behaviors. And so that's something that I represented like that. And so this is what we call a phase diagram. So sometimes we are not so much interested in the specific values that these observables take, but we want to know what is the phase diagram. Just let me give you an example and a motivation for that. So imagine that you have a material, you're doing an experiment, and then all of a sudden this material, it's a superconductor. So it has a wonderful property at very high temperature. And now you want to use it for something. You want to build something with that. You want to make a device. However, the temperature, I mean, you know, that if it's superconductor, it means that it can conduct electricity without losses. So that's fantastic. So we can now store electricity for a very long while there, for days, without losing them. However, it may happen that the temperature is still too high in the sense that in order to reach that, we have to cool down, and it costs a lot of money or a lot of energy to cool it down. So it's more expensive to cool it down than what we gain just by having the electricity without losses there. So maybe what you would like to do is to say, well, I would like to understand this material and to design it in such a way that now by changing some of the parameters or doping it or putting something, now the temperature goes up. So it's still superconducting at room temperature, because then we will like to build it. And then people in condensed matter, they say, okay, so let's try to understand this material. So let's take and make what we believe. So we know that there are electrons, and there are electrons with this property. We have a lattice like there. So let's write a Hamiltonian. And then they write a phenomenological model for this material. And then they would like to know whether this phenomenological model that is not coming from first principle, is phenomenological. They just come up with a Hamiltonian. They would like to know if it describes the experiments, if it describes what they see in the experiment. So what they have to do is to solve the Hamiltonian, answer these questions, and compare it with experiments. And if it coincides, then you get evidence, and then you can take the Hamiltonian and play with the Hamiltonian and see how to raise the temperature. However, the first problem is difficult, because they cannot solve this Hamiltonian, and they cannot see if this phenomenological Hamiltonian corresponds to the physical observation that they are having. This is what happens, for example, with the Hubbard model. You know, it's supposed to describe high-TC superconductivity. However, since we cannot solve it, we cannot check it. And so maybe we have to add now nearest neighbor interaction and so on. And so we don't know. And so that's the typical problem that may appear. No, it's not only that you want to solve a problem because you want to predict some physics, it's that maybe even the Hamiltonian itself, you want to make sure that this corresponds to the physical situation. And that's why what people measure are these kind of phase diagrams. They measure superconducting, non-superconducting, and something like that. So you would like also to get these phase diagrams now for your Hamiltonian, because then you can compare with your experiments, gain confidence that that's the Hamiltonian that is describing phenomenological your system, and then play with that. So sometimes, I mean, many of these properties that appear that are very exotic occur at zero temperature. That's why we single out here from the thermal equilibrium state, the one that corresponds to zero temperature. And in that case, we have the phase diagram at zero temperature. So now it could have, for example, U and maybe an H, and the same things will happen. So depending on your values, then the observables may be zero in some places or have different properties. And so what typically happens is that each of these regions here is called a phase. This is why it's called a phase diagram. And so what we have is that regions separated by lines. And these regions are what are called gap phases. And so now I go back. I'm sorry for the camera that has to go back and forth. But so I want to go here and so define a property here, which is called the gap. So now I told you what is the ground state energy. That's the lowest eigenvalue in the spectrum of your Hamiltonian. And so now we can look at what is the first eigenvalue. So this will be this one, E1. And the gap is defined, delta, as E1 minus E0. This is called the gap of the Hamiltonian. It's just the energy difference between the first eigenstate and the second eigenstate. And so there are some systems in which you increase the size of your system. You increase the size of your system, like I was telling you here, you grow n, grow n, but the gap stays. So the energy of the ground state and the energy of the first excited state is lower bounded. The difference is lower bounded by a constant. This is what we call a gap system. Okay, gaps. So this means that delta, the gap, as a function of n, is larger than constant, larger than zero. And so what we have in physical systems is that there are these gap phases, and every time that we go from one phase to another one, so when we change the physical properties, what happens is that the gap closes in the thermodynamic limit. So here, the gap is zero. This is what is called gapless. So this would be, in the whole line here, this would be gapless. And in physics, we are interested in knowing not only the gap phases, but also the gapless phases. They are very interesting in themselves because they are critical. So something very extraordinary happens with these phases. They have long-range correlation functions and so on, and sometimes we are interested in that. And I wanted to tell you that because whenever we talk about quantum algorithms, these quantum algorithms, some of them will work depending on whether you have a gap or you don't have a gap. And now, these gapless that appear here, now what is very relevant from the computational point of view is how the gap closes when n increases. And so what happens is that in most of the interesting cases, at least that I know, for critical system, this gap closes, like 1 over poly n. And then there are some, let's say, weird behaviors that are not critical, in which this can be exponential in n. And so you see already at what I'm hinting at. So is that when we talk about ground state problems, then with a solving with a quantum computer, then it may happen that we may be able to, even though this is a QMA hard problem, to answer questions about the ground state. For these particular ones, if they are gap or they are gapless and they are critical, meaning that the gap scales in this particular one, then adiabatic kind of algorithms will give you the solution and will solve the problem that I posed before in polynomial time. Whereas the fact that they are gapped and the fact that they have a gap that decreases like 1 over poly n doesn't help much in classical algorithms. And that's, again, one of the swift points where a quantum computer can help a lot because it can solve problems that we don't know how to solve in classical computers. So, I mean, maybe, finishing up with that. So, as you see, I'm a physicist, and you can notice that, and that's why I'm not trying to make connection between the difficulty of the problems and complexity classes and so on. So, I'm being very practical, saying that, this is what we know how to do with classical computers, and this is this we cannot do, we don't know how to do with classical computers, but whereas with quantum computers we know how to do that, and that's where the kind of quantum supremacy can come in these problems, because then we can address some of the problems that you cannot solve with classical computers. So I think that I will make a break here for questions, because then the next thing is that I'll start just I will give then quantum algorithms for these 3 problems, different kind of quantum algorithms. And yeah, so any question?
In the last picture, so is the gap only closed on the lines, or is there also a whole phase?
No, on the line.
Only on the line.
Okay,
and
so
on
we have
the lines.
We have phases. So what happens is that, of course, I draw 2 parameters. There might be many parameters, and so what you will have like a volumes that are gapped, and the surfaces will be gapless to go from one to the other one. So it can happen that now your particular problem is moving all the time on a critical region. This happens with XY models and things like that. But that's what I wanted to represent.
Could you explain again why you have this concentration and energy density there? Like, does that just follow from locality and translational invariance?
Say again? What?
Why do you have this concentration and energy density?
Oh, yes. So actually you can compute what is the width, and this is given based, you have to impose, the way of doing that is that without loss of generality, you can impose that the trace of HL is equal to 0. Because if it's different than 0, you can add a constant here, and constant don't change anything. So if you take that, this means that the mean energy, if you compute just the trace of your Hamiltonian, this will tell you where is the center of this, the average energy with respect to all the states. This will be somewhere, and then you can compute what is the trace of h squared, will tell you what is the width, and the trace of h squared, if you compute it here, would be the sum in lambda and lambda prime of trace of h lambda prime, right? But you see that if these 2 terms don't have an intersection in the support, this will be 0, because the trace of each of them is 0. So this is just the sum on lambda, and lambda prime having some common support, in this case like n. So then the width will be the square root of that, which is the square root of n. So it's coming from that. It's very simple to show.
Hi, thank you so much. I have a question about the states of interest that you've been talking about. So my background's in computer science for context. So you mentioned like dynamics is where you have the state after some time, and you have e to the minus I ht. But you also said something about the thermodynamic or like thermal equilibrium being something that's achieved if you like let the system go. So that confused me a bit because I thought like if you let the system go, you get the like first one, the dynamics case by like Schrödinger's equation. So how do you get the thermal equilibrium?
Right. So what happens is that now when we have one of these materials, this is not completely isolated. So in reality, it's coupled to the whole rest of the universe. And so if you would like now to write what is the evolution of the whole universe, it will get difficult. But this is why in statistical mechanics, making some assumptions, that you can see that if you wait for a long time, because the energy is conserved, the energy of the whole universe, the Hamiltonian of the whole universe is conserved, then at the end, what you will have is something that will have certain energy, and then this is described by that using kind of James' principle of maximum entropy. Okay, so that's kind of one of the postulates of quantum statistical mechanics, that now you let the system evolve with the environment, the whole environment, and wait, then you just can assume that it's in that state. Of course, this is not a derivation, but it's coming just from, I mean, other let's say, postulates.
So for the last diagram, or last thing that you commented on, there's a triple point essentially in your phase diagram. So I've got two questions. One, there's a triple point.
Where are you? Can you raise your hand? Oh, yeah.
You're almost looking at me, so I assumed you could see. Yeah, so there's a triple point in your phase diagram. So I've got two questions. One is, do you have something like closing the gap as you go along the gapless lines?
Well, I don't want to enter now on the details of triple points or double points, so maybe it's something that you can discuss
The other one
later.
might also be similar. I was wondering if you could comment on the difference between when the gap closes inverse polynomially and inverse
well, I mean,
exponential.
we know examples. So you have critical systems, then it typically decreases like 1 divided by the size to some critical exponent. And now there are some pathological examples for which we know that you can do it also exponential, but I mean, I cannot tell you more than that. Yeah.
Okay, thanks.
Thank you. So I also had a question about just to understand the connection with the gap and the different phases. So my naive understanding is that to identify a phase, usually we look at some parameter that does not vanish. That, let's say, when one parameter vanishes and when it does not vanish, it identifies different phases. That's what I remember for all classes. And so the connection with the gap is that sometimes those boundary will be defined with the way the gap vanishes. So it's two different concepts, or they are related?
No. Okay, so I mean, this is entering a little bit more physical details. So now you have these gap phases, and then there are the gapless phase. Now you can move in a gapless phase, and even in the gapless phase, you can go from a gapless phase to another gapless phase. And so what happens is that if it's gapless, it means that, I mean, morally speaking, the ground state is degenerate. And if there's the regenerate, what can happen is that you can break some of the symmetries of your Hamiltonian, and you have a symmetry broken state. And this means that there is an expectation value of some observable. It should be 0 according to the symmetries, but because of the degeneracy, it's not 0. So this is not to be confused with what I was saying, that in the phase, you're interested in some properties like superconductivity or something like that, which is just a property that occurs there in the ground state, that it's not related to symmetries.
Okay, thank you.
Okay, so maybe, so maybe I move on, maybe with a remark that I also wanted to say, and maybe I come to that later on, that if you talk to physicists working on these problems, so sometimes they don't care so much on this, how things scale with n, but they are interested in what they call the thermodynamic limit. So what this means in this context is that what they will, where do I have it? Right, so here. So this will depend on n. So this quantity will depend on n, and this quantity will depend on n. And so what they would like to find, what is the limit when n goes to infinite now of this quantity? There. Or the same thing from the ground state. So that's the quantity of interest. So this is what you would like to extract. So why are they interested in that? Because you have a material like that there will be 10 to the 30 electrons or 10 to the 32 electrons, many, many, many. And so you just work with 22. This will not be very good. So this is why they want to know what happens in the limit. And of course, now if you talk about complexity of finding some thermodynamic limit, you cannot talk about complexity of n because n does not enter the problem. So in that case, and so people have been looking at that, what you can say is what is the complexity in terms of 1 over epsilon. Okay, so what you can see is that imagine that you have one of these, you are interested in computing the expectation value of sigma x on one particular point in the ground state in the limit when n going to infinite. So this is one value. And if I give you that epsilon is equal to 1, that's very simple, right? Because, I mean, it's, the value is between -1 and 1, so I give you 0, and then I get the right result. If I tell you that it's 0.5, then it will make, maybe it's a little bit more difficult. If I tell you that it's epsilon, then the computational time that will take you to give me this value will depend on 1 over epsilon. And now you can check in a classical computer or in a quantum computer what is the computational time as a function of 1 over epsilon. And maybe in a classical computer it's exponential of 1 over epsilon. In a quantum computer it's polynomial over 1 over epsilon. And then there will be where the advantage is. So what I wanted to say is that this complexity that typically is formulated in terms of growing the size of the system, for some of the physical problems is not so relevant, but is more relevant, yes, the complexity in terms of the epsilon in the thermodynamic limit, even though both things are related to each other, because in order to get the value to get this limit, then probably I will have to do some kind of extrapolation. And if I do this extrapolation, I will have to grow system sizes. And so at the end, I will have to have a good scaling with the system size. But I'm not going to talk about that. Okay, so now I will talk a little bit about quantum algorithms. And so they're all very simple as compared to what we heard this morning, at least if you're a physicist like me. But anyway, so I will start giving quantum algorithms for finding the ground state. Well, first of all, I will give you a very general quantum algorithm that doesn't care. First of all, I start with the dynamics, and that will be relatively simple. That's actually what Feynman already did, and Seth Lloyd put it in a rigorous framework. And then I'll talk about ground states, and then I'll give a quantum algorithm that works for arbitrary problems, but it's exponential. So the computational time grows exponentially with the number of qubits or the size of your system. And then I will tell you some other heuristic algorithms, but these heuristic algorithms are very useful because if you have the conditions that I told you before in physical problems, like the gap scales in some particular way, then they are promised to work. Okay, so I start now with quantum algorithms for the dynamics. And the basic idea is now that we would like to compute psi of t, which is e to the minus I ht acting on sub psi 0, where this is an easy to prepare. So the quantum computer, we assume that this can prepare it easily, like a product state, for example. So this is what I wrote here, easy. And then we are giving this call observable, this operator, that we want to compute the expectation value. And the basic idea is to take your quantum computer, prepare in this state, then have a quantum algorithm that would prepare your quantum computer in this state, and then you will measure this quantity, then you repeat it many times, and at the end you take the average value, and we know that the error in the average value will decrease like 1 divided by square root of the number of the repetitions. So we have some epsilon, then we'll have to repeat 1 over epsilon square, the same process. So the only question that remains, that is non-trivial here, is how to design a quantum circuit that would do the time evolution. And this was done already a long time ago. And let me give you the idea. Probably most of you are familiar with that. Let me take first the simplest case this is the Hamiltonian. I remind you that each of these h lambda is acting on a qubit and around. I will use the word qubits now, but it will be it could be qubits in general. And let's imagine first the simplest case in which these Hamiltonians commute with each other. And because this is extremely simple, because then we have that e to the minus iht, since they commute, we can write it as a product of e to the minus I h lambda times t. So what we have is that in order to prepare the final state, what we can do is to apply first one of the local Hamiltonians, I mean the dynamics of the one of the local Hamiltonians, then the next one, then the next one, the next sequentially, and this will give us the state. And so the only thing is that we have to know is how to implement the evolution with this Hamiltonian, but this Hamiltonian is acting on a qubit on few qubits around, so it's a unitary transformation acting on a constant number of qubits, and we know how to decompose it in terms of gates, in which the number of gates will increase exponentially with the number of qubits that I have here, but since I have a fixed number, that it doesn't matter, it's a constant time. So you see that this can be done in constant time. Well, I'll have to do it n times, so I'll have to do something here, something here, something here, something here, something here. I can do it even in parallel because they commute, so this is extremely efficient. Now, what happens in the general case that they don't commute with each other? Then we can use something that is called product formulas. Or in jargon is called trotterization. And the basic idea is that if we have e to the, let's say, minus I, HA, T, HA plus HB, let me explain it like that, then we can approximate it by that. And the error that we make can be upper bounded by some constant that depends on t square, and also the commutator of HA and HB. That's something that is easy to derive. I mean, you can do the exercise. You just take this quantity, take the second derivative as a function of time, and then you integrate it, then you can write it like that plus something, and this something is this part that is it's an upper bound. So you can easily find. It's a very simple formula. And so now we can use this formula sequentially. So what we can do, let me do it in one dimension, but you can do it in more general. So imagine that you have now one of the Hamiltonian X here, the second Hamiltonian X here, the third Hamiltonian is here, and so on. So you have like odd Hamiltonians and even Hamiltonians, so that you can write HA as the sum, and right here, H even, and HB are the Hamiltonians that are H odd. And if we do that, then we see that when we look at the commutator of H even and H odd, then H even will meet a couple of H odds only, otherwise this will be 0. So the number of terms that we have here is of the order of n. So this goes like n. And now, equipped with that, what we can do is to take now the whole Hamiltonian. Thank you. And of course, this grows very fast with t, but what we can do is to pay a little price by writing as e to the I ha plus hb times t divided by m to the power m. So I didn't do anything. And now, you see, I just take divided by m, but to the power m. So there's no problem because h commutes with itself, so I can do that. And now, for this, I use this formula. So the error that I can make here would be like this t square. So it will be the new t, which is this quantity, is t divided by m square times n. And so this means that this can be approximated or can be equal to e to the minus I h a t divided by m, e to the minus I h b t divided by m to the power m plus some error, which is this t squared divided by m squared times n. And this is already written in terms of gates, because you see, this is acting only on the b's. So this corresponds to performing a 2-qubit gate, a 2-qubit gate, 2-qubit gate, 2-qubit gates. The HAs are 2-qubit gates, 2-qubit gates, 2-qubit gates, 2-qubit gates. And we have to do it m times. So this is a sequence of 2-qubit gates. And we have to make sure only that this error is sufficiently small. So we can check, we can take and of course, there is an m, sorry. There is an m, because I am doing an m times, so there is an m. So we have to take m like n times t squared divided by epsilon. And then we can make sure that this error here is epsilon. So what we see is that in order to evolve with the whole Hamiltonian, we can do small evolutions with small time steps of the order of m, and this m is proportional to n t squared epsilon. And so the gate complexity of that, so this is the number of times, then every time that you do one of these steps, there are n gates, so it will be like n squared t squared, which is polynomial. Okay, so this will be the number of gates to prepare this state with an error epsilon. And once you have this state, then you measure that and you repeat it many times, and then you can see how the errors accumulate and do the error. But at the end, what you see is that everything scales polynomially with n and with t. In fact, that's not the best algorithm. There are better algorithms for that. So one way of improving this algorithm is to take higher Trotter expansions. So instead of writing this, you can write here e to the minus another b, another a, another b, another b, and take this t smaller. And if you do that, then actually you can have an error that scales now like n times t divided by epsilon. And then there is even a better method if you use some other ideas that is not based on product formulas, which has the scaling, which is n times t log over 1 over epsilon. So the whole summary is that with this simple method trotterization, that's a method that we know already for many, many, many years, and that was the one that was proposed already by Seth Lloyd many years ago, this will give us an efficient algorithm, efficient in n, size of the system, in the time that we want to simulate, and in epsilon to compute that quantity efficiently. However, for these problems of evolution, if you want to solve it now with a classical computer, typically you will have to do an exact diagonalization, so you'll have to use Lanczos, so you'll have to solve some differential equations, and these differential equations, they are of the order of 2 to the n, so the computational time will grow exponentially with n. So that's the, let's say, the clearest example where there is a huge advantage by using a quantum computer as respect to a classical computer. And maybe, I mean, emphasizing a little bit this advantage, I mean, I don't know, I think that Scott Aronson and some other people have formalized that, but so here, if we compare the computational time in a classical computer, in a quantum computer, we see this exponential speed up with a quantum computer. But we could think also in terms of memory, because in a classical computer, if we want to solve that, we will need also an exponential memory. So you have now you'll have an exponential memory as well as an exponential time. Okay, so it's not only that you have some exponential time, it's also an exponential memory. You want to solve that. And that's what is intrinsic quantum mechanically. When we solve with quantum computer optimization problems, there might be, or some other problems, some classical problems, there might be exponential speed-ups in terms of time. But here, just because of the nature of the problem, we get right and for free an exponential gain with respect to the memory. So you could ask now, so what happens if we change a little bit the questions and we allow to solve this problem with a classical computer only allowing for linear memory? There will be an overhead in time. And so the overhead in time means that now it will take not only exponential in n, but it will be exponential in n times the depth of your system. So it would be, if the depth of the system, so if the time is of the order of n, this will be super exponential with respect to that. So that's what people have claimed many times, and you hear very often, that quantum computers, quantum simulations are extremely useful if you want to solve dynamical problems. And that's why there's something that is difficult with classical computer, whereas for quantum computers it's kind of straightforward. And that's also what people say, is that probably, the first simulations or quantum simulations that will be, let's say, useful will be of the dynamics of many body systems, because they are very hard for classical computers, and for quantum computers are natural. However, one can now go a step beyond and say, so what are interesting problems for dynamics and physics? Okay, and there are not that many. There are not that many, actually. They're relatively few. And one of the reasons, at least that I think, is that people have not asked questions about the dynamics. They were always asking questions about evolution, because in many of the systems, about the thermal equilibrium, because of the question that we had before, that I told you that these systems are permanently interacting with an environment and keeping it in thermal equilibrium, and therefore, since they are not isolated, then these questions don't come, because it will have to include the whole evolution with the environment, and this will be just the whole universe, basically. This will be very difficult. However, now there are experiments done in materials, but also in atomic physics and so on, in which they have isolated so well the systems that they are really described in terms of some Hamiltonian. And that's why, in order to answer these scientific questions that are posed by these experiments, I think that they are now starting to come up these kind of questions that are interesting for the dynamics and where quantum computers can help. So with this, maybe the last 5 minutes for questions, and then I'll move on to the ground state and thermal equilibrium. So some questions?
I didn't quite manage to understand what you tried doing there with the M.
Okay, so if I do this formula here, then this will scale an error which would be t squared times n. So this means that I can only run 4 times of the order of 1 divided square root of n. And this would be very bad. You see, you want this error to be small. So if you do it directly, you take the time and do this trotterization, this kind of approximation, then this is not going to work, because this will mean that t squared times n has to be small.
Yeah.
So we want to overcome that. And to overcome that problem, then we cut it in small
So you
pieces.
reduce it by m?
So what we do is the total time. This is the time that you want to simulate. We cut it in m pieces.
Okay.
And so one of the pieces is t divided by m. And so we use this formula here. And by using this formula here, then we can get the arbitrary times with polynomial.
Okay, thank you very
effort.
much.
Yeah.
Hi. It's related to the last comment you made. So in this dynamics problem, we start from a easy to prepare state, right? Yeah. Do you have any example of the many body system naturally starting from those easy to prepare states?
Right. Okay, so easy to prepare states would be states that are either in thermal equilibrium or the ground states or product states. So for example, in this many-body system, when you want to study dynamics, you start with cold atoms or with some materials, you start with a very simple state where there are no interactions. And so this corresponds to the thermal state without interaction, this corresponds to a product state. And then you quench, you switch on the Hamiltonian, or you open the current, or you do something, and then they start evolving. That's one particular case in which people have been interested in the dynamics, that you start with something where they don't interact, and you switch on the interactions, and then they start evolving. But you could also have, people have been studying quenches, in which what you do is that you prepare adiabatically some state, with the adiabatic algorithm that I'll explain later on, and then you quench, you change suddenly your Hamiltonian, and then you evolve with that Hamiltonian. And so those are, let's say, easy to prepare states.
Okay, so a quick follow-up question is that, let's say if you can do that for many easy to prepare states, is there any clever way to use that result to simulate the, let's say, superposition of those easy to prepare states?
So what I will show later on is that for thermal states, for thermal equilibrium, actually that's the trick. That you start doing for easy to prepare states, and then you average, and then you get what is the expectation value for some not easy to prepare state. So this will come later on.
Yeah, thank you.
So Ignacio, I have a question about your last comment about the exponential complexity in memory.
Yeah.
So there's this famous result of Kitaev that says that actually a quantum computer can be simulated in P space.
Yes.
By basically always sampling from the Feynman integral. So how is this compatible with that statement?
No. But the question is, what is the time? So the time.
No, but the memory requirement should not scale. Does not scale exponentially. That's what you said.
No. What I'm saying is that if you try to solve this in your classical computer, you will store naively, you will store all the coefficients. Wait a second. All the coefficients, and then it will take an exponential time. Now, there is a way of using only linear space, because it's in P space in particular. But then you will have to pay some price in time. And so you'll have, the time will not be exponential, let's say in n and t or something like that, but they will be also in n times t. And so that's why it makes it more difficult.
In evaluating the expectation value of the operator, is it also efficient? So the dynamics are efficient, but the evaluation of the operator is also efficient.
Right. So this is what I went very fast over that. So once you can prepare the state, you prepare the state, then this will be a local observable or two observables, so you just have to measure them. And then, because you will get one bit of information if you want, you have to get now the expectation value, you have to repeat it many times, but the error will decrease like 1 divided square root of the number of repetitions, and so you can just repeat it whatever time. The complexity means that it will be like proportional to 1 over epsilon squared.
Hi, thanks for the talk. I wanted to ask, how do you do the whole thing for time-dependent Hamiltonians?
Oh, very good question, and that's important because I wanted to mention that. Yeah. Okay, so if these are time-dependent Hamiltonians, you can also now, in a time-dependent Hamiltonian, what we have is a time order. Time order, so let me write it here. So the evolution would be the time order e to the minus I integral 0t ht prime dt prime. But this by definition is just a trotterization. So this is by definition e to the minus I h at t1 delta t1 delta t e to the minus I h at tn delta t, and this is the limit when delta t goes to 0. Okay, so the time order is defined as the product at different times. So what you can do is without, as long as this h doesn't change much in delta t, you can fix it to some value. This will give you some error, but you can put it in the budget of the error. And now the rest, you do it like the trotterization because it's similar. And so this means that you can also use that in time-dependent Hamiltonians. The only thing that you have to make sure is that the time steps that you're doing are such that the Hamiltonian is more or less constant in each of the time steps. So you will have a Hamiltonian which has a frequency that is very large. Then, of course, it will cost something, but this will be a constant factor. It will depend on what is the frequency in which things are oscillating.
Okay, thanks. Yeah. Okay.
Okay, so I think that we stop here, and so we'll come after the break.